Before we get started, our TA Stephen has a quick announcement.
All right.
Quick advertisement.
Hello, I'm TA Stephen. Basically, I run a club here at UB. It's called UB Musicians. We do basically jam sessions for, like, if you play drums, bass, guitar, or if you sing, come on down. These are located at SU room 302 on Wednesdays from 5 to 7 p.m. They're pretty chill. They're laid back. We have a drum kit. We have a bunch of amps. And yeah, we're also offering group lessons from Friday from 5 p.m. to 7 p.m. Same room, 3rd floor of SU, room 302. Yeah, you can talk to me if you're interested in it. We are in the process of getting a community guitar, or we do private lessons, which are in the process of being organized. But yeah, that's it. Enjoy your lecture.
Before we get into some content, does anybody have general questions, comments, concerns? Yes.
For the homework, I got the main objective homework, but some of the tests didn't necessarily do. How much does that matter?
It's a good question. I don't have a solid answer for you, but the primary objective definitely weighs the most. Let me give you a more concrete answer in a second here. It's because I set up the auto grader like that to give you the one if you got the primary objective, regardless of your testing. And for the verification of the homework, that's the most important thing we'll look at. If it does come down, if you get the primary and it does come down to you didn't do enough testing for the objectives, or there is something up with that, we'll follow up with you and say, and give you another chance to verify that and make sure. I might set up the future homeworks a little different, just to make that more clear. Right? If those 3 objectives are fine and it's just a matter of testing, we can work with that. But the primary objective, it's named the primary for a reason. That is the actual goal of the assignment. So if you got that and everything's fine. You said physics engine, right? Rhyming dictionary. So that, yeah, either way, it does imply that you completed the other 3 objectives, that you have proper functionality in that, which is the main thing. It's an application objective. You applied the course content to a real-world problem. At that point, I'm fine. But if there is some deeper seated issue, if there are actually errors, and maybe I just didn't test for them in the primary, but that would be follow-ups. I wouldn't just say, surprise, you didn't get that in those cases. And that's the way it'll work for learning objectives too. If you're ever a boundary case, if you just flat out didn't do half the lecture questions or something, that's an easy no. If you did all the lecture questions and were good in the TA interview and did the lab activity next week, that's an easy yes. If you're in one of those middling situations, if you're a borderline situation, I'm not just going to outright say, no, you didn't do this objective, good luck on the final, but I'll follow up with you and say, hey, it looks like you're lacking in this bullet point. Let's talk about it. Let's see what you can do to prove to me that you do understand that bullet point. So I don't want any just surprises. If you're putting a good faith effort in the course, you shouldn't get any surprise. You're surprised you failed that objective. That's not my intent. That's not my goal. So I know with the grading structure, it's going to look a little stressful. I realize that it looks stressful from your perspective. There's a lot of question marks. But I'm not looking to screw anyone over. If you truly did complete the objectives and you're understanding the course material, you should go low stress, and I'll work with you if you ever are in one of those borderline cases. So hopefully that at least puts you at ease. And if you ever feel that's not true, contact me, bombard me after lecture. Do what you got to do to make sure you're not treated unfairly in the grading, that you didn't get any surprises. Then I might just say, well, look, you had 300 submissions for every lecture question. I might give you an explanation. I might not always give you the credit, but we'll come across all those situations as they come. Any other questions or any follow-ups on that? Yes.
The dictionary should be, it doesn't say that it needs to,
because you did sort.
I sorted it.
The order shouldn't matter. In my testing, I'll sort both lists, both my expected and your output, and then check. If you do sort, you won't be penalized for that. So you might have something else going on in that.
Yeah, it's like the application, like when you type into the GUI, it's fine, but I don't know why it's failing. I'll figure it out.
Right, yeah, that's more of an officer's question. We can talk. But the sorting shouldn't matter. The order shouldn't matter. You'd hit .random on it. Random ordering. My grader will be able to find that. Be able to see that. Anything else? Let's get into it. So we're going to talk about stack and heap memory again today, and we'll see more examples on Friday. But the stack and heap memory, I can't exactly write a lecture question that's going to test your understanding of stack and heap. I can kind of implicitly through references, through object references, but next week in lab you can count on drawing out the stack and heap memory. The TAs will give you a program, and you'll be expected to be able to trace through that program, be able to tell what's going on the stack, what's going on the heap, how the references move around, and be able to explain all those things. It's not really something I can have a lecture question for, so next week's lab, that's really where the stack and heap, that third bullet point for the learning objective is going to be. So you can expect that in lab. For the lecture question, I'm going to hit you with the references again. Here we're going to have 3 classes. We're going to work with references of these classes. So for this, we're going to have 3 classes. One, a class named valuable, which is going to represent some valuable item that a person can own in this case. It has no constructor parameters, it has no methods, it has no state variables. It's just basically kind of nothing. It's just a thing. It's just a valuable. So we'll talk about, and that's the crux of this homework. How do we work with that? We don't have anything, we can't do some valuable dot whatever. What do we do? How do we work with it? How do we test it specifically? A class named trader. This is going to represent a person who owns one valuable item, and they're willing to trade that item with another trader. They're willing to swap items, and they can only have one item at a time. No data structures here, just one item. They take that item as the parameter of their constructor, and that item is going to be named exactly item lowercase I. So since this has a clearly defined name, in your testing you can access that variable, because we're all going to name it. You're going to name an item, I'm going to name an item on Autolab. My correct and incorrect solutions are all going to name an item. So that's defined. In your tests you can create a trader, and then do trader1, whatever you name your variable, dot item, equals, throw that in an insert. That's all valid testing. It has a defined name, we can test that. Then, and that's it. That's all for the trader class. No extra methods, no extra state variables. And then finally, a class named trade agreement, which is going to be when 2 traders agree to trade their items, and then they can swap these items between each other. So to enter into a trade agreement, we're going to create a new object of type trade agreement. The constructor is going to take 2 traders that are willing to trade, so new trade agreement of trader 1, trader 2. That's going to say these traders are agreeing to this trade. And then one method, execute trade, which will actually swap the items that they agreed to trade. So whatever item each trader currently owns in their item variable, they're going to switch those items. This trade can only be executed once, so 2 traders enter into an agreement. They execute that trade. Calling execute trade again doesn't do anything. They can't swap these items back and forth as you keep calling execute trade. It's not really how trade agreements work. One agreement, one trade, calling the method after that, that should be disabled. So a little bit of extra functionality there. And the question is, the crux of this problem, I suppose, is when that trade is executed, making sure that those items of type valuable, are traded by reference. So we don't want to have a trade happen and have 2 people have similar objects to what the other person had. We want these to be the exact same objects. It should refer to the same object in heap space. It should be that exact valuable item that they had. So even if we had extra state variables in the valuable class, maybe we have a description and a price, maybe quantity, maybe something else, some other properties, and after the trade you have something with all the same properties, That's not good enough. It has to be the exact same thing. Maybe there's some value to that exact item. We don't want a duplicate of it. So for example, if somebody has a diamond, it doesn't matter that after the trade, the other person has a diamond, the same size, the same color, the same clarity. We don't want that. We want that exact diamond. And we're going to check that by the references. So when we have two items, in our case, the valuables, if we check them using equal, equal, if we have two variables, maybe item 1, item 2, they're both of type valuable, and we say do these two things equal each other with equal, equal, that's going to check if they refer to the same object. So since we don't have any like item 1 dot description, like there's nothing to access there. So we're going to check if they're the same item by reference, and you do that using the equal, equal operator. So if I have a trader, I can say trader1 dot item, assert trader1 dot item equal, equal the item that I expect you to currently own. And that's how we can write these tests. So we want to check those by reference. Default behavior of equal, equal is check, do these two variables refer to the same exact object? That's the default behavior. In the next upcoming weeks, we can override this behavior and give it different features to equal, equal. But by default, do these two variables refer to the same exact object in heap space? Do they have the same reference? Are they referring to the same place in memory? So that's how we can work with valuables. Check if we have this references to the exact right variable without having any variables to check. Check it by reference. Any questions on the question itself? All right. Let's talk about stack and heap again. So last time we saw an example of the stack. We had one method call, we put one stack frame on the stack. That stack frame returned to resolve to a value. We saw one loop, we entered some scoping issues and things like that, and then returned to main. With objects, we created one object, put it on the heap, went through it really quick at the end of lecture, put it on the heap, passed a reference to that object in a method. That method made a change to one of its variables. That method ended, the stack frame was destroyed, the reference that we gave it was destroyed through the parameter, but we could still see that change in the main method. So let's take these same two ideas and just look at more complex examples. We're going to put multiple objects on the heap first. We're going to see multiple frames on the stack and see how all these interactions work and what some of the implications are of these concepts. So yeah, I know this example is getting a little dated. It's the problem with doing topical examples, but let's talk about birds and boxes. So here I have a quick program. I won't explain all the details right here because we're going to step through this line by line. But we have a class named bird with a couple variables in a method, a class named box with a constructor that takes two birds in a method, and a main method that's going to instantiate these things, instantiate objects from these classes, and work with them a little bit. So let's step through this and see exactly what happens when this program runs. What's happening in memory, what goes on the stack, what goes on the heap, what's going on here. So first, the very first thing we do, we're jumping right into it by creating a new bird and accessing some heap space. So when our program starts, we get our stack. We get our stack from the operating system where we can put all our variables as we're running through this. And the very first thing we're doing here is saying, hey, operating system, I need some heap space. Stack's not going to cut it for me in this program. Whenever we see the keyword new, that's what we're doing. We're going to the operating system, we're going to the JVM, saying, hey, we need some space. I need enough space to store a bird needs enough space to store 2 ints. Give me that space. I'm going to create those variables for a bird, all of the state variables, and then the new operator, that keyword, technically not an operator, but that keyword is going to return a reference to that object that was created during that call to the constructor. So I get this reference, which here, again, I just chose random numbers, but we get some reference to some place, some reference that tells us how to access this place in memory. That's what's returned, and that's what we're storing in this value named bird of type bird. So this value goes on the stack, and it stores a reference to this bird that was created, that has those two variables that from the bird class. Next line, we create a variable named action of type string and assign it the value nothing. And I gotta get my disclaimer here. The strings technically do not go on the stack. We're going to gloss over this detail for 116. We're going to pretend strings go on the stack. If in lab you do want to do the correct thing and how strings are represented in memory, feel free. If you do understand that and want to show it off, please do. But for our purposes, we'll just pretend that strings go on the stack because that's the way they end up behaving in our programs. What I really want to emphasize is why the stack and heap affects us as programmers. And if we think of strings as being on the stack, we're going to get the same behavior from strings. Strings are going to behave the same way as ints, doubles, etc., things that go on the stack. Even though they are technically in heap space, but they are immutable, meaning they cannot change, just like our lists. They can't change, so we don't have those reference features. We can't give a method a string, have that method modify our string, and have that modification show, that side effect show elsewhere in our program. We don't have that property because of the immutability. So if we pretend, using imagination, that they're on the stack, we can kind of get away with that. In future classes, this might become more important that you have to know that they're on the heap, but for our purposes, we're going to pretend they're on the stack. So with that disclaimer, because some of my colleagues get mad at me when I do this, I say, I don't care. But anyway, some people do get upset with that. So I want to make sure that disclaimer's up there. This is technically not how it's represented, but we're going to pretend it is and move on so we can focus on what we want to focus on in this course and what we want to understand. So string, pretending it's on the stack, value nothing. Then we hit our conditional. Our condition for our conditional is a method call. So we're going to start a new stack frame. From our bird object, we're going to use the dot operator, which means go to that object on the heap and call this method from that object. So from this object, we're calling in danger. So from this bird, we're calling in danger. So when we call in danger and we're checking times checked, and I still didn't update it. And I could have this dot times checked to make that absolutely clear that it's a state variable. But we're going to times checked. When we access times checked, since we're calling from this bird on the heap, we're going to access this times checked variable, increment it by 1, and return true. Since we return true, our conditional was true, so we're going to run the if part of this block. We're going to create a new value named action of type string and set it to the value panic. Here we saw this last time. Since we declared a new variable of type action, since we already had a variable of type action, this seems like a conflict, but since we're in a different block, these are completely different variables. This is the action variable in this block. This is the action variable in this block. So this is the action variable in this stack frame. This is this stack frame, and this is the action variable that can only be seen from within this block. So when we access action from inside this if block, we're going to find this action, assign it the value panic, then we hit the end of our if, destroys everything that was declared within that conditional, and then when we get to this print line, the only action left on the stack is that one that holds nothing. It was never modified, never changed, so we actually didn't do anything when we set that equal to panic. Nothing was changed outside of that block. So now that we're outside of that block and we print action, we're just printing the string nothing to the screen. This next line is where a lot of the action happens. So here we got quite a bit going on in one line. Let's piece this apart and see what's going on here and see some more complex interactions with the heap. So we're eventually creating a value named box that's going to be assigned whatever this new resolves to. So what does new resolve to? We're going to create a new box, so we need to allocate space for a box. But before we can do that, we have to allocate a new bird. So the first thing that happens, we're going to create a new bird and put that on the heap. Go back to our OS, go back to the JVM and say, hey, need some memory, I got a bird I got to create. Give me some space for a bird. It's going to give us space for a bird. Create those two variables, times helpful and times checked. And these variables, they have the same name, but they're in a different scope as our other object. They're in completely different spaces in memory. They have the same name. That's all they have in common. Completely different variables. Every time we create a new object of a type, it gets its own copies of all of the state variables. So I have a new bird. New returns this reference. That reference goes right into the constructor call. So nowhere in my main method do I have a reference to this bird that I just created. I only have access to it through that box that was created. So this box is going to have access to this bird. So this box value of bird 2 is that reference to this new bird. And the value of bird 1 is going to be the reference to this original bird because we use this bird, which was this bird, which is on the stack, which stores that reference. So we were able to create a new box with this bird that we created up here, and also a brand new bird that we won't have a reference to anywhere outside of our box. Finally, we create that variable named box and assign it the return value of the new, that constructor call. We get this reference, which was wherever our operating system decided to give us memory to be able to store this box. So we put that box, get that box reference, store that in the variable named box, and that box reference has the references to the two birds. So we have two ways to access this bird. Only one way to access this bird, and only one way to access this box through everything that's in memory. Any questions on this line? A lot of stuff happened on that line. All right, I'll stop again at the end of the program and let us all digest what happened. All right, we hit this conditional. We got to resolve this, this condition. And at this point, we're going to have multiple frames on the stack. We're going to gloss over this just a little bit. I'll explain it, but the next example is where we're going to put a lot of frames on the stack. That's where we really want to talk about that. For now, yeah, we went to the box variable, used the dot operator, which means follow your reference to the object that you refer to. So we're going to say box, jump to your object. In this object, from this box, we're going to call in danger. From this method call in this stack frame, we're going to call bird1.inDanger. So we're going to go bird1 dot follow your reference, get to this bird, and then call in danger from this bird. We're going to get to times checked. That's this times checked because that's the reference that we followed is this object, and increment this times checked by 1. Return true, go to bird 2. So bird 2, follow your reference, find bird 2, increment your times checked, return true and true, so we get true, and we're going to execute this line in the conditional. We're going to enter this if block, we're going to execute this line, action equals stay in vote. Now this time, a little bit different from the previous one, we're not declaring a new variable named action. We're not using var. So we're just saying, hey, I have a variable named action, assign it the value stay in vote. So we're going to look at the stack, look at this if block. I don't see any variable named action there, so our program's going to look outside of that scope, look at the stack frame in this case, find a variable named action, and overwrite its value. So now this action is going to have the value stay in vote after that line's called. So now this time we do actually see this change outside of that block of code because we didn't have another variable named action. And then when we print line here, now we're getting that stay in vote. There's only one variable named action. It's right here. It has the value stay in vote. So we're going to print that to the screen. We reach the end of our program, give everything back to the operating system. We're done with that memory. So a good amount of stuff going on here. Let's take a second to digest. Anybody have any questions about this one? Yes?
How does the bird 1 in danger is like equal to the bird 2 in
Oh, what is this, you mean? So this is a logical and. I'm saying if both of these are true, return true. Otherwise false. Is that what you were asking?
Are they both true?
Yeah, so in danger for the bird class always returns true. It's not even checking anything, it's just always returning true. So the last expression that's evaluated in this in danger is just true. So I have true and true. So I'm going to return true. Yeah, as far as software goes, this is not an interesting program. Just always a method that always returns true and things like that. Yeah, question?
Why don't we include a variable for times checked if we're never going to access times checked?
If we're never going to access times checked?
Was that just for showing heap and stack, or was that?
Yeah, that's what I'm saying. This program doesn't do anything interesting. None of this makes sense as far as a program goes. I just want to show some heap stuff. Some heap and stack. Yeah, we have a method that always returns true, times checked, but we never ask a bird how many times it's been checked. We have a value that's just initialized to 0 that doesn't do anything. Yeah, there's a lot of things as far as software goes, doesn't make sense. It makes sense if you watch the movie though. Yeah. But that's about it. I was just going for the references on this one. Yeah, references. Ew. Any other questions on this? All right. So let's look at another example. Let's talk about multiple frames on the stack. For this, I want to clarify the expectations at this point. So we have another recursive method here. We have a method that calls itself, so it's going to be a recursive method. I do expect you to be able to follow today's example and the other recursive method that I showed. You should be able to trace through, kind of walk along with me as I go through the execution line by line. I do not expect you to be able to write recursive methods at this point. Later on in the course, that is a topic that we'll talk about. I will ask you to write recursive methods, but at this point, that's not an expectation. There's no reasonable way that I can expect you to be able to write recursive methods. That's a huge leap. I can barely expect you to trace through the execution of one, but I do expect you, when I walk through the trace of the execution, that you'll be able to follow along with me. So just to make that clear, I know recursion can be a very slippery topic. It takes a long time to really wrap your head around it. Just know that, yes, I'm using recursive examples, but I'm doing that just to get you, mostly to get you familiar with recursion, just get you this idea in your heads that recursion is a thing that exists and it's kind of tricky. That's all I want you to see by these recursive examples. And kind of as another motive, it makes it really easy and compact. I have not much code here, but we're going to get a lot of frames on the stack, and I want to talk about those frames. Recursive examples just are a good way to be able to get a lot of frames on the stack real quick without a lot of code. But no, I don't expect you to be able to write recursive methods at this point. That'll be quite a bit later in the course. So don't panic is what I'm saying. So let's walk through the execution of this thing. I want to compute the geometric sum of 3. Geometric sum is the sum of all the values 1 to n. So of 3, I should be summing 1 plus 2 plus 3. That's what this method should be doing. And I expect this to be returning 6 to me. So let's step through. I claim that this will return 6. Let's step through the execution and see that it does in fact do that, and how and why it does return 6, why it does compute the correct thing. So the very first thing we do, if the main stack frame, very first thing we're going to do is create another stack frame. Technically, we already got 2 frames on the stack. Success, yes. So compute geometric sum of 3, create a new stack frame for this method call. Every time we have a method call, we're creating an isolated environment with its own variables that, and it can't access variables outside of that stack frame. So we create this stack frame for this method call, and we start by creating a variable for each parameter, only one parameter in this case, n. So we're going to create a variable for n and assign it the value of the argument and put that on the stack inside the new stack frame. So I have my parameter n, assign it the argument 3, put that on the stack frame, and then start executing the method.
This entire method is just a conditional. I have one conditional that's going to tell me what I'm going to return, either run this code or just return 0. So here, my n is 3. 3 greater than 0 is true. So I'm going to execute this. The very first thing we do inside the if block, we enter the if block. The very first thing we do in the if block is create another stack frame, create another variable n, and assign it this value 2. We have 3 minus 1, we're going to get 2. So we create a new if block, new stack frame, new variable n. N is 2. We're going to call this method again. N greater than 0. N in this stack frame is 2. True. Go for another stack frame. Inside another if block, inside another stack frame. Put those on the stack, create a new n for the new method call, the new parameter with the new argument. N is 1 in this stack frame, so we're going to be true. We're going to call compute geometric sum again with the value 1. True. New if block, new stack frame, new parameter with a new value. Now when we get to compute geometric sum, we start running the method. When we check that conditional, we have 0 greater than 0, false. So we're just going to return 0. When we start talking about recursion, this is going to be what's called the base case of our recursion, meaning that this is a condition within our recursive method which is not going to call itself. And this is where we finally start returning. So if we don't have a base case, we're just going to keep calling and calling and calling, adding frames on the stack, frame, until we get ourselves in trouble. But here, since we hit our base case, we're going to destroy this stack frame, remove it from the stack, and return 0 from this stack frame. So this stack frame is destroyed, this value of n is destroyed, and we're going to return 0 in this case. And notice that we have a lot of values of n on the stack, but since these are all in different stack frames, we're not bothered by that. Each time, whenever we're in a stack frame, we're going to look at the value of n inside that stack frame. And we can't even access the other values of n, the other variables of type n, so we're not even aware of their existence, so they're not going to mess us up. We're not going to have this trouble of why are there so many n's on the stack. They're all in different stack frames, so no big deal. So now we're back in this stack frame that we were in before. Last time we were in this stack frame, we were waiting for this method call to resolve. Well, that method call just resolved. Its stack frame returned us a value. So now we can resume execution in this stack frame and keep going through this method call. So this resolved to 0. So we're going to create a variable named result of type int, assign it the value 0, and put that on the stack inside of our if block. We're going to hit result plus equals n. Result, we're going to look inside the if block. We're going to find a variable named result, value 0, plus n. We're going to look for n. We don't find one in the if block. Expand our search, find a value for n, a variable named n right here inside the stack frame. There's no chance that we can find these values of n, so no worries. We're going to find this value of n, 0 plus 1, and reassign that to result. We hit the end of this method call. We're going to return result. That's going to destroy this entire stack frame. We're going to return 1 from this method call. That puts us back in this stack frame. This stack frame was waiting for this method to finish, to resolve. It just resolved and it returned 1. So now we can resume execution in this stack frame. Each stack frame is going to remember where it left off. So when we go back to these stack frames, we can pick up where we left off and keep running the program. Keep running inside this stack frame, running the program, and running our code. So here we returned 1. Result equals 1. Result plus n. Now when we add n, we're looking at this value of n, which happens, this variable n, which happens to store 2. So now we have 1 plus 2. Return that 3. This whole stack frame's gone. We're in this stack frame. Result equals 3. 3 plus n. Well, there's only one n left, but the n in this stack frame, its value is 3. 3 plus 3. We're going to return that 6. We return that 6 back to the main method. the main method and the main block was waiting on this method call. That method call and its stack frame just returned 6. So we can pick up right here where we left off, result equals 6, and just print 6 to the screen. Any questions on this example? Came up in the other lectures, so it's worth mentioning here. If I gave you a question, or just anywhere, or if you're writing some code, and you had the problem of computing geometric sum of n, you really shouldn't use recursion for this example. I use recursion because I want to show a bunch of frames, stack frames, and talk about the stack memory. For this one, it's better off, you're going to be better off just running a loop. Writing a loop, iterate from 1 to n, sum all those values, done. The one problem here with recursion is as you're running, we have all this stack space that we're using up. It's not memory efficient at all. It's very inefficient in terms of memory. We have to have a lot of stack frames. We have to have n stack frames on the stack at one point. So that can get pretty inefficient. So most cases, a lot of cases, you don't want to use recursion because it's going to take up more space during the execution of that program. So just worth mentioning, worth throwing out there. This is not an application where you really want to use recursion. We will see when we do talk about recursion proper, we will see examples where recursion is our hero, where it makes it a lot easier, where we wouldn't really feasibly be able to get away with a loop. But we'll get there in due time. And our program's gone. So during this execution, we had this conditional, which determined when we're going to hit our base case, and that base case determined when we're going to start destroying stack frames and returning back up the recursion. But what if we didn't? So what if we had this with no conditional, and every single call to geometric sum created another call to geometric sum, so every stack frame is creating another stack frame forever. Now let's jump back to execution, where we had n equals 0. This is where our condition was false and we hit our base case. So now we don't hit our base case, there is none. We're just going to call compute geometric sum again. We're going to put another frame on the stack. N is -1. That's going to put another frame on the stack with -2. And eventually we're going to reach the end of our stack space. We're going to get to this area that's either used by another program or is otherwise reserved by the OS. It's not allocated for us. We're going to hit that and get our big stack overflow error. So when we use up all of our stack space and try to use that next byte of memory that we're not allowed to access, we're going to get stack overflow error and our program crashes. These are very bad errors. When we do get into recursion, whenever you see a stack overflow error, it's almost always because you didn't have a good base case to your recursion. You were never hitting your base case, and you just went infinite with your recursion. And it gave you stack space until you used it all up. And then the program crashes. So let's take a look at this. Let me run this example. We expect this to return 6 as I claim. Yes, it does work. So I want to show us something. I'll show more examples of this on Friday, but I want to at least give you a taste of it today. We have 10 minutes left of running what's called the debugger. This is a very useful tool for programmers. This is something that can save you hours of debugging. It can help you out a lot. So let's just see what this thing is. So first I'm going to set what's called a breakpoint. I'm going to go into the sidebar here and just click to make a red dot in the sidebar. This is what's called a breakpoint. And now when I run my program, instead of using the green play button, I'm going to hit this green bug, this bug icon, or you can go in the sidebar, right click and go to the debug option. But we're going to run our program in the debugger, and it's going to walk through our program one line at a time and show us the values at all of our variables. The debugger is a very powerful tool. It can do a lot more but we're going to focus on being able to inspect all the values in our variables at any time. So if we start our program, let me just step through a few times. We have this button here, this arrow, which is going to make one step. It's going to step through one piece of our program at a time and walk us through each thing that's happening. So I can walk through this program. We can see what's going on. Let me just get a little bit into this. And what we can see as we step through this program are all of the stack frames that are on the stack right now and where they left off for each computation. So these three, we see they're stuck on line 9. They're all waiting on line 9 for that execution of compute geometric sum to resolve. And if I look my current execution, I can look at my variables here. I have a variable named n with a value 0, but I can also look at each of these stack frames. If I go to this stack frame that called the current stack frame, I have a variable named n with the value 1. If I look at this stack frame, I have a variable named n with a value 2, n with a value 3, all the way to my main method, which doesn't have anything interesting. It has the command line arguments, but we don't have any, so it's just an empty array. Then we can keep stepping through this, and we can see these starting to return. As we step through this execution, we can see our stack frames being destroyed, returned, until we finally get back to our main method, print the result, and end. So those examples that we walked through today, the examples we walked through on Monday too, you can do the same thing with any code you have, any examples you have. You can walk through them with the debugger, see what the state of the stack is, where your stack frames are, what your variable values are, what's on the heap, which we'll see in a second here, and see all of that stuff. So what I'm showing you on the slides, it's not just magic, it's not make-believe. You can actually physically see in any of your programs how that memory is being managed. Highly recommended when you're trying to debug something. If you're running code and it's just not giving you the behavior you want, try stepping through your program and seeing what those values are at any given time. It can save you hours and hours of code. Cannot stress enough how much time this can save you. It's one of those things any developer, the first time they discover the debugger, it's just such a relief. Like, just productivity goes through the roof after that. Instead of banging your head against errors constantly, you just set a breakpoint and see what's going on. You don't have to just, okay, print line X, print line, all your variable names. None of that anymore. Just run the debugger. You can see everything, all of the values at any time. So let's do the same thing with our bird box. I'm going to set a breakpoint down here. Oh, I forgot to mention in the last example. When you run the debugger, you can hit this or right click. When you run the debugger, it's going to run your program as usual until it hits your breakpoint. So the last one, I set the breakpoint at the first line of main, so it just stopped right away and let me step through the whole program. Here I'm going to set my breakpoint a little bit lower, so it's going to run all of this part of my program, but once it hits this line, it's going to stop, it's going to pause, and it's going to show me the values of everything and the current state of the execution of my program, including stack frames, variables, and the heap space. And what I want to show right now is that heap space. So I want one more step. I want to get through this line. And we can see the birds being created when it creates these variables and initializes them. You can see that any code outside of all the methods is going to be ran when we create a new instance of a class, a new object of a type. So if you do want some extra initialization code, just put it outside of all the methods, and all of that code will be executed when you create a new object of this type. It doesn't have to just be the state variables. You can have some extra logic there too. We could have method calls. We could even create new objects in here. Any code, any valid code is fine. Runs the box. And at this point, I want to start opening this stuff up and seeing what's going on here. So we only have one meaningful frame on the stack for this one. But what we have, see the variable bird that we created. It shows us the values of those variables at this bird, but it's actually going to the heap space and getting those values for us to show them. But we want to see here, this right here, we have a value of type week3.memory.bird at the reference 954. That's telling us this is on the heap, and we have some reference to it so we can access that in heap space. So we have some bird at 954. If we look at our box, we have our box at 959, and the bird 1 in that box is the same value, 954. It's the same reference as that value in bird. So we can verify, we can actually check and make sure our references are matching up the way we expect them to be. Bird 1 in the box has that value. Let me expand these. And bird, that variable, also has that value. So and these variables are going to be the same because these refer to the same exact object. So these variables are going to be the same because they refer to the same object. Sometimes they might just happen to be the same, but here they are the same because they refer to the same exact object. You guys want to skip 115 and start 116? It's something. And the other bird is 957. So this is an actual different bird. This is a different object in heap space. So we can see that difference and the different variables from there, from those objects. Call our methods, call our stack frames. And we can see when we call this method, I won't step through each of those, but we do see times checked here, changed to 2 in 954, and our 954 up here, that also changed to 2. It's referring to the same object in heap space. That variable was changed, it went to heap space and changed that. And also we have that 1 on bird 2. We got that times checked incrementing. And one more thing, if I can find my action. Just to verify what I said earlier, it is a nuanced point, but these strings, these are on the heap. We have a reference, 963 for the string. Again, we're not going to worry too much about that in this course, but strings are going in heap space as well. They're not going on the stack. All right, any questions after all that? All right, see everyone Friday.